All right, awesome. But yeah, this whole like next like this lesson and like 5 lessons in is like neural networks. So we're going to do like, we're going to do basically introduce neural networks today, which is kind of like the hot kind of stuff of like machine learning right now. We'll kind of talk about like why that is. And I've debated a little bit of like how exactly to present it, because I think everyone presents it in a very different way. Curriculum presents it one way to introduce it. I have a certain way like I like to kind of talk about it. I've seen other ways to talk about it. So we'll kind of say like what these parts are and where it comes from. And also just another like video set, which I think is like does a really great job of explaining like the concept of like neural networks, like why this would work. In the end, it ends up being like calculus, like in math, which it looks really intimidating, to be quite honest. But a lot of times it's actually not that bad. Like, and to be quite honest, again, is that a lot of times we're using packages where we don't have to do the full mathematics every time for ourselves. But it's useful to understand how these processes work mathematically, so you can understand where the issues can kind of come up or the limitations of like what you're doing, right?
Okay.
But yeah, so what we're going to start off like this first lesson is going to be about introduction to neural networks. I'm going to talk about like the general concept of them and like why we go through it. I might even look at the curriculum particularly to show you like what those look like. And then we'll dive into next lesson more like deeper, like they call it like deep neural nets, which basically it's like uses a lot of different like we'll talk about what these are, but basically like a lot of different like nodes basically to figure out more and more information. And then we'll get into something that I think is really cool is convolutional neural networks, which are like using neural networks and using things called convolutional layers, which basically takes information from pictures and tries to translate, like the way I kind of summarize it is that it'll take a picture, and a computer doesn't like really know what a picture is. It just knows numbers of a picture, which are from its pixels. So it looks at each pixel, going left to right across the screen. That this is number, 132. And this one is like, well, I guess 132, but like depending like what the value is, like it'd be like, this is like 8, this is 12, this is 14. And that's what color it is. And basically convolutional neural networks allow you to take, instead of the pure information, and translate it into say what's in the picture, which is really interesting, the way it works out. And it turns out they're pretty powerful. They're one of the big reasons why image detection and image recognition is a lot better than it has been in the past few years. So that'll be kind of like coming up, and then we'll explore a little more about neural networks and how you can apply it. And then later, I think next week we'll talk about like applying it to neural networks. And next week we only have 2 study groups, and then that's all of the lessons we actually have for this module. So it actually comes by pretty quickly. So you're pretty close to being done after this week. So with like information.
Okay.
Yeah. Which I don't know, is exciting, but also maybe a little, a little
Yeah, it's a
kind of
little
intimidating.
intimidating.
Yeah. Of course, that doesn't mean like you've learned all of machine learning, data science, done with forever, but you'll definitely have like all of the, like I say, the big stepping stones of moving forward and being able to go into the next part. So something to look forward to. So yeah, so we're going to talk about the neural networks today. And this is, to be honest, like most places probably would want to start off with this because it's really cool and it's a really awesome thing you can do. They actually, well, we'll talk about like what neural networks can do, but basically, if you remember back, like all the way back when we did linear regression is kind of like is like kind of like the stepping stone of all machine learning, really, and like what you can do. But with machine learning, or not machine learning, with linear regression, you really have to like know what features to use. You can't like, and you spend a lot of time building these features, making sure what things will work out well. And I say linear regression, I could also mean like polynomial regression, right? But basically the idea is like you have to like tweak it the right way and understand like what the underlying theory is and stuff like that. What's kind of cool with neural networks is that by its nature, you more or less kind of just give it the features and it kind of figures out what things are important and what going through. There's still some stuff you have to do on before feeding in the information to the neural network, but it's not as much like hand holding as it is for like linear regression, where you really have to, if you don't come up with a good linear regression model features, nothing will ever happen. Neural networks, it can figure out, though sometimes you kind of have to give it the right kind of setup. And that's actually what the hard part is making sure the setup's correct so it can actually figure it out on its own and how much time you can put it through it. So we're going to go a little bit there. So I'm going to start sharing my screen. Oops, click the wrong thing. There we go. And so there we are. And I gotta grab my window back. Okay, cool. So you should be able to see it says starting with perceptrons with a perceptron.
Yeah.
Awesome. So this is actually really interesting. At least I think it's really interesting, is that the idea of neural networks in particular actually were back in the 1950s when it was first presented. But there's a couple of reasons why neural networks weren't really used, even though the concept kind of existed pretty early on. And one of the reasons is that they just didn't have the hardware. You couldn't like do the things that they wanted to do because it just would take a computer way too long. And in the past few years, computers have gotten to this point where we can process a lot of information. Ironically, I don't know if ironically is the right word, but a lot of the things we do with neural networks, we started with GPUs, graphics processing units. And GPUs, funny enough, were mostly used for like visuals and stuff, a lot of times for like gaming and stuff like that. So it's kind of interesting to see like a gaming platform basically kind of allowed these neural networks to be trained really well. And then now we have even more specialized hardware. Like, for example, I think Google has their thing called their TPUs, which are basically tensor processing unit, basically dedicated towards what's called actually doing neural networks, deep learning and stuff kind of going through. So we're getting more specialized hardware, but that's the one reason why it took a while for us to actually do this. And the second reason is actually having enough data. It turns out between like all the different machine learning algorithms, neural networks just really don't do all that well a lot of times with small amounts of data. There's ways you can circumvent that. And there's a lot of like areas of research right now say like, what do you do if you don't have as much data? And saying like, how do you approach that? But for the most part, it ends up being the more data you have, the better. And without less data, your model just might not do very well. But you need a lot of data usually to do really well with a neural network. So these are a couple of reasons why these things actually haven't really done better or took so long, even though the concept existed for a while. So starting with a perceptron, I'll just show you this diagram. So this is kind of like the idea of a perceptron, which is actually really like simple in that sense of like what is going on. But basically you have like this X1, X2, X3. And basically you're feeding this into, like you can think of those like your features, your inputs. You're feeding these inputs into some mathematical, like decision mathematical equation. And you say, okay, we put in the output. So what's interesting is that the way this looks is, I'm just going to draw it or write it out directly on here. So what's interesting, basically it's something along the lines where you say, okay, I have some value, W1, times X1, the feature, plus W2, X2, right, another feature, and then W3, X3. Okay, and then usually we have something called a bias, which is like this little extra part, and sometimes I call it just W0, but you could sometimes you see as B or something like that. And this right here, basically this right here comes out as our output. Like if you look at that, that actually doesn't look very intimidating at all. Like if you see like all these different parts. And this is like, you look how it's very similar to linear regression. So like this by itself, this is the idea of a perceptron. It's like you take an input and you make an output going forward. So, and then what's interesting is that because usually we talk about classification, we can basically do something called an activation function. So we wrap this whole value, whatever this output is in here. And so you can think right here, it's like, here's our output. And whatever this thing is usually output like a little sigma, because usually we use something called a sigmoid. We'll talk about that in a second. Basically, we have some kind of function that says, all right, whatever this value is in here, it's going to be some number. Whatever that number is, basically convert to either a 0 or a 1. And that's going to be like our activation. So if you imagine this is our activation function. This basically says on or off. Okay, 0 or 1, or say 1 or 0, right? So on being 1, off being 0. And what's interesting is that we can actually have activation functions that don't just do 0 or 1, like a step function. We can actually have something that's like a between 0 and 1. So it could be like, oh, a 0.8. It's like, well, it's mostly on, or like, he's like, oh, it's kind of, you know, like this much value. And basically you can take that value and you can say, okay, is it this thing or not? And this right here is usually referred to as the perceptron. Sometimes you would just have just x1, x2, but you could have any, what's it called? Any number of inputs. It doesn't have to be 3, it doesn't have to be 2, it could technically be 1. And basically we have these values here. These are not excluding W0. You can think of W0 as kind of being like all by itself, it's just a number. But you can see like this W1, W2, W3. The reason why we call it a W is because it's usually referred to as weights. Basically saying how much does this X1 matter. So you can imagine like X1 times how much it matters, W1, and X2, how much does X2 matter. So these are different weights. And a lot of times we'll actually see the notation with being like the weights times the columns, and sometimes we'll have it like transpose. But the main thing is like, oh, we'll keep all the weights within a column vector, and then we'll have like our X right here as our vectors, and this will make an output of basically the same number of vectors coming out. Okay, or sorry, not numbers of vectors. This will just be a number. Output. So that way you basically have this part. And so with that, it's like that's kind of like the whole idea of a perceptron, which is actually, if you think about it, not super complicated, right? Like it doesn't seem huge amount. And this is where it's kind of nice, the simplicity of it actually allows us to do really complicated things. Kind of some background on the perceptron. This is actually kind of based on the, what's it called? The concept of neurons. So that's kind of, here's like neural network neurons, where we have things like neurons that are connected together. I don't know if how familiar with biology in that sense, but if you have like a neuron and another neuron basically together and they both fire, you have something like the dendrite right here. I'm not sure if I'm a good biologist, but like I'm gonna say dendrite. I'm probably wrong, but basically it would detect those signals and says, oh, if those signal together, then it would send a signal down, and that would carry out through the next part. And basically that's the whole concept of like the neural network or neurons. It's not really like it's not like, I want to make this really clear. It's not literally biology, like how it works, but it's inspired by it. Sometimes people also can debate about saying, oh, what are you actually doing in a neuron? But all that stuff. You have a question, Hassan, or comment?
Kind of just referencing it. So when you put in all your data and then you get it weighted and you kind of put it all together in one number, you get the 1 or the 0. So
more or less, yeah. Mm-hmm.
So the answer that you're getting isn't like the answer you're literally getting. It's the whole series of like, okay, you get a 1 here, a 0 here, and leads to this, and leads to this, and leads to this.
Yeah, and that's,
okay.
Yeah, and I'll show that in a second too, because right now it's like, oh, you only have essentially a yes or no question right now, which is kind of limiting, right? But let's say, for example, if you, like the classic example is like handwritten numbers. If say, okay, is this handwritten number a 2, a 3, or a 4, or a 5? This would be like saying this output is saying right here is like, is this a 3? You know, and you can interpret as 1. If it's 1, it means it's super confident. It's like nearly 100% confident that it's a 3. If it's closer to like 0.5, it's like, well, it thinks it's a 3, but it's, you know, it's not as certain. And then when it gets closer to 0, it's getting closer, saying it's probably not a 3. So that's kind of like the interpretation of this between 0 and 1 kind of deal. Later on, we'll find we can combine these multiple parts, and we can actually say, okay, well, is it a 3 or a 4? You know, or a 5 or a 6 or a 7. And basically you can layer these on. And that's what we'll talk about with an actual neural network itself. So let me go ahead and show you that, since we're kind of leading right into it, is that you can kind of think of like, I can make a couple like little graphs of like, you know, these points, like how you classify them. In this case, you could probably like, you know, very quickly write like a linear regression and like basically, oops, there we go. We can actually like write like a little line that would separate this out more or less. So we can use linear regression, like logistic regression, right? To actually do a nice separable line and everything like that. We can use other machine learning tricks and stuff like that. When it gets more complicated though, is when we have something like this, where there's no direct shape that we can like at least quickly say, oh, it needs to be this quick shape kind of deal. And that's when things get really complicated. And it's actually where neural networks do a really great job and trying to figure out this complexity. And so in order to figure out this complexity, basically we put in more complexity into here. So I'm actually going to zoom this in a little bit. So let's go ahead and make this bigger. So this here, you can kind of see like right here by itself, if I am drawing, you can see this guy right here. You can see this more or less like the perceptron going forward, right? You can see, oh, there's an input here, okay, and there's some outputs going here. And then you can see, like, for example, if I go just look at this specific one and I ignore what this is, you can see like, oh, look, like it has an output going out. And when they have these different arrows all going out from this one node, basically it's like if this is a number, it's just the same number being processed through and weighted. But you can see like at the very end here, that's literally like our perceptron right there, right? And what's interesting is that we can basically take all these different perceptrons, and we don't really usually call them perceptrons at this point, but essentially you can connect them together into this network, right? This neural net. And what's cool about that then is that we can actually say, okay, let's take in different values like x1, x2, x3, okay? We can basically put in like an extra, like, you know, weighting to it if we wanted to. And this will provide some number in here. And then we can basically say, well, how much does this x3 value actually affect this node right here? So this has a certain weight. So it's like, okay, this one, like, okay, this one actually really matters a whole lot. It's like, okay, let's say it gives it like, I don't know, 0.7, okay? And this one's like, okay, this one doesn't matter as much. We'll give it like a 0.3. It's like, okay, and then figure out this one. It's like, oh, this one, you know, kind of, we'll give it like a 0.4. You know, and so you have this one value coming out and spreading out to these different values, but it's not just this value, it's also added up from these other ones. So what's happening here, like in this one specific node, so I'll focus on here. Oh, just clear, there we go. Okay, so let's focus on like this one specific node. This specific node essentially is saying, okay, there's an x1, and we'll just ignore this very first part. We'll just say this is x1, this is x2, this is x3. And say, okay, from x1 to here, there's a w1 output, okay? And then over here, we'll just say this to here is a w2 output, okay? And then this one to here is a w3 output, okay? And basically, this one node right here, we can call this a node now, this value in here is just simply that x1 times w1 plus x2 times w2, you know, and so on, plus x3, w3, okay? And that would be the one value here. And each of these w1s, w2, w3 would have different values, okay? So you'll notice, like, okay, that means we get all the inputs in here. To get this one right here, you'll notice that we'll actually have different values, right? Like this line right here, well, this would be like a different w1. So generally we'll like have different naming conventions. So for example, we'll have like this one say, oh, it's not w1, we'll say it's like 1, 1. Saying it's, oh, going to the first layer node from 1. So we can keep track of it. But the idea here is that each of these arrows represents a different amount of weight. So you can imagine there's a new weight for this one, a new weight for this one, a new weight for this one, which will produce a different number than this up here. So even though it's using the same inputs, it'll have a different kind of value. So this value might be like higher or something like that. And they usually range from between 0 and 1, okay?
So the equation would be like x1 1 plus x2 2. Okay.
That's right. Yeah. So basically each one would have like essentially that little like linear sum together. And then once you have this value, you essentially say, okay, from, let's say we have this purple value right here. Okay. And we start off from there. Well, this one would actually, you know, feed forward into the next one. So you can see like, oh, this will have a weight that will go into this node right here. This one will go into this one right here with a different weight. And this one right here will go into this one with a different weight. And then you can see there's a fourth one here in this case that goes in this one. And then you can see this like one node, for example, takes in all those 4 inputs and go forward. And some might be really close to 0. Some might be really close to 1. Some might be in between there, you know, with the different weights. And we go through. There's one part in here that's kind of like not really obvious. There's also always like a little extra bias that puts in, and it's just a constant number. It's not affected by x1, x2. So you can think of like this is like B1, B2, B3, B4. Oh, I'm repeating some stuff. No, that's right, because there's 4 different ones. So you can see like there's basically just an extra constant. So you'd add this extra constant, like B1. And that's kind of like equivalent to like if you think like linear regression, Like that's kind of like your y-intercept. It's like that extra little part. And this, we call it the bias. Basically, it's like bias in the sense that we're pushing it towards a certain value, right? No matter what x1, x2, x3 are, b1 will never be different. It will always be the same number every time. And so basically you can figure this out. And then at the very end here, you can have something like, like what the number is. So this is kind of interesting. So let's say it's like a hand-drawn number. It can either be a 0, a 1, a 2, or a 3. And let's say that we don't count. There's no 4 or 5. So there's only 0, 1, 2, and 3 people drew out. Basically, you can think of these parts saying, okay, how likely, like this number between 0 and 1, for example, say how likely is this number drawn out as 0? How likely is it a 1? How likely is it a 2? How likely is it a 3? And it combines these parts to say, oh, therefore, it must be a 2, or whatever number it ends up being. And so this is the idea where we can actually figure out, like hopefully this conceptually makes a lot of sense. Like, okay, from these different parts, we can basically have different weights and stuff. And essentially what it is that you could create this yourself, but you can see how kind of complicated it can be with like adjusting the W1, W2, adjusting this part, adjusting the bias. Like if you think of how many different little like parameters, we call them hyperparameters, right? But like all these different parameters we can change and little dials and stuff, it would take a long ass time. Like it would take a long time to figure out, how to make it sure it's exactly right. And what's interesting is it's like, well, we don't even know if it would actually work. What was really cool is that a neural network is actually like a general function estimator. Basically, it can create any function you want. You just have to know what the right, parameters, the right little dials and stuff. But you can theoretically make this neural network make any value you want. Now, obviously, like, if we only have like one node, like if you had one perceptron before, you only have so many values. You probably couldn't do whatever you want. So you can kind of think as you get more complexity, if you add more and more like layers, for example, here's one layer right here. We call it the hidden layer because it's not on the input, it's not on the output. You can think of like the hidden layer right here. And having more basically nodes, more layers, more parts in here, basically the more complexity you have, the more availability for the different parameters you can adjust and adjust and adjust and adjust and to get more and more complexity. So it's kind of cool is that you can actually make any function you want. And when I say function, I think that like more in the mathematical terms, we'll also call it like a mapping or a function. But basically you can think of it, it's like whatever input you have, it takes it to an output space. And these output spaces, as long as they can be represented by some kind of number, is that you can basically figure that out. And it doesn't have to be like a nice, pretty function. A mapping could be like, oh, these parts right here is like mapping these parts. It's like, okay, all of this will be inside that green, like those labels. Like that's kind of like, it doesn't have to be not continuous. It doesn't have to be like a nice, pretty function. It can make any mapping you want, which is what we need for really complicated parts. So this is why this is super powerful by itself. So this is the concept of like what neural networks are. You have any questions about anything I kind of went over on this part?
No, I think I got it. There's questions I have thinking of like the implementation, but we haven't really got to that. So I think I get the concept.
Yeah, and right now it's like I haven't shown you like how it works, like how to do this, right? And the key part that you should really question yourself, you're like, how do I figure out what these W1s are? And that's really what it comes down to. So this process I kind of showed you like moving forward, like pushing things forward, that's called a feed-forward process, which you can think is pretty simple, right? You just basically take these different numbers that are already specified, you multiply together, you add them together. You might have an activation function that says, basically squishes that number to between 0 and 1 and basically going forward and just moving it forward. And that's kind of what the feed forward. So the feed forward like part of a neural network is usually pretty quick because essentially you push all the numbers through and computers can compute that very quickly. The hard part is figuring out, well, okay, once you have these numbers out here, you can basically compare it with some value at the end. So you're like, okay, it says it's a 2, but really it was a 3, And so you're like, okay, like, oh, that wasn't quite right. So the way we kind of represent this, though, is like, well, how do we represent saying, this is different from each other? We kind of take one step back before this part, and you can think like this is 0, 1, 2, or 3, right? So you can actually think of this as a vector. And saying, for example, like let's say this number right here gives like, oh, that number gave like 0.1, super small, like, right? It's like probably not a 0. It's like, oh, but it gave like 1, like, you know, because, oh, 0.3. So there is some chance it was a 1, but not for sure. And then for 2, it's, oh, 0. Let's say 7. And then for 3, let's just say it gave like 0.6. Okay, so in the end, 0.7 was the most, the 2 was the most likely thing, so it said it was a 2. But in reality, it was a 3. So the way we compare this with another vector is the actual vector, like what it should be. It's like, well, it's not a 0, it's not a 1, it's not a 2, it is in fact a 3. Okay, and basically we can take the difference between these parts, subtract this difference, and essentially use this difference between the two to figure out and say, okay, this is how far off you were. It's like, oh, you gave like the 2 a 0.7. Oh, that's not right. You should definitely lower that value. Like that value needs to be much closer to 0. And this 0.6, that really should be closer to 1. And this right here is basically our cost function. And this is how much we like our loss and cost function. Basically, we use those functions now to assess how well our network did. And we use something which we'll talk about in a second called backpropagation. And basically, we propagate this error, this like loss error. Basically, we propagate it back to fix the best way possible. And we say best way, basically the efficient way possible, according to gradient descent. But basically, we propagate this error backwards. Say, all right, fix this, change the values, adjust the values a little bit more, and then try again. And then it'll say, oh, you didn't do it so well. All right, let's go ahead, change the errors and send it back, and then readjust and go back and forth, back and forth.
Those wouldn't be the biases, would they?
Biases too. You could also change biases. So all the different numbers that are on here, basically, like basically everything that's non-x could be changed. And so you can imagine like all the different possibilities. There's just from this like relatively small network, because these networks can be very, very large. But you think right here is like, okay, there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 already inputs just from this one layer, right? And then each one of those input layers also have a bias on here. So that ends up being 16 different terms just from this one layer. And all those values can be adjusted from 0 to 1, right? Like you can imagine that would, and it could be negative too. So like you can imagine just being like adjusting this like crazy. And this is where the idea of backpropagation comes from, is that basically you take this loss, this error, how bad was your model, and say, okay, let's go ahead and let's rewind the clock, basically figuring out where you went wrong. And say, okay, you went wrong this way. Let's adjust these parts and run it forward again. And then do the backpropagation, run it forward, backpropagation, run it forward. So you can do this over and over again, basically, to fix your model to see how well it does. Okay. And those are like the broad strokes of like how a neural network works. But I think it's an important thing to do, because otherwise it's all math in the end, which we'll see backpropagation basically is doing the chain rule of the derivatives going backwards. But it's important to know like why you're doing it. So that's kind of like the overall thing. And I wanted to show real quickly what this actually like looks like, which TensorFlow, let's see here. Nope, that's not one. I probably had it saved, but I didn't. TensorFlow playground. Oh, it's it. Sorry. So TensorFlow is a framework. I think it's developed by Google. Here we go. Okay. TensorFlow, here, I'm going to show you the simple one first instead of the one that actually works. So it's kind of cool is that basically TensorFlow is a framework, a library that allows you to basically do a lot of this stuff really easily. So they also have this little playground just to kind of show you the concept of what a neural network is. So it's actually referenced in the curriculum, but I want to show you what it is. So but basically there's a few things going on here. Is that you can think of these parts as our actual neural network. So these are like the nodes I showed. So you can imagine like, we have different inputs, for example, and then we can have like, let's say 2 hidden layers. So let's say we have like 4 right here. And then we'll have like, 2. Basically these 2 parts represent, is it orange or is it blue? Okay. And we have our data set. You can see like there's different data sets right here. And we say, okay, we want the network to figure out what's it called? What is orange and what is blue? Okay. And so we have these inputs going through here, and you can see like these inputs are saying, are they close? Like, it doesn't really matter too much exactly what these are, but you can think of these ones right here as saying, oh, how close is it to this? Is it yes or no? on this, spectrum. For example, this is orange, this is blue, or whatever, right? And so you can put these inputs in. You can also, like, they're just showing, like, you do a train test split that you normally would do with machine learning. There's something we didn't really talk about, which is the learning rate. So we can figure out for backpropagation, for gradient descent, what the learning rate is. Our activation, you can see, for example, like ReLU is pretty common. But basically, it just says, like, adjust it from from 0 to 1. Basically, like what this value should be. And then we can basically just feed this through. So what's kind of cool, we can actually run this and we can actually kind of see, like, so what's going to happen, you can see this if I hover over here, you can see the weights right here are changed from like 0.23. These are just random. And I can actually click this, edit this, and actually increase or decrease it. So for example, if I increase this being a value, let's see if I can, you can see I can make the value very, very high on this part, right? And you can see it's like, oh, -12. That means that this has a really strong strength and it'll actually push this forward, okay? But we can also just have this move forward. So what's gonna happen when I press play here, basically it'll run through it once, see how well it does. Like, oh, didn't do very well. It'll send the error back with backpropagation and then run forward again, back and forth, increasing every time it goes back, basically changing the weights until things look good for it, okay? So if I run this now, just kind of show you, you can see right here, this weight's gonna change significantly, and you can see it's not doing very well. And actually, I'm going to stop this because I've set that to really high. It'll take forever. But you can see here the different weights. For example, you can see it's getting really good at this. But you can see, like, for example, the weight from here to here is very close to 0. It basically had no effect on this part. But this part actually fed forward. And this one actually is getting very, very little. So you can see the relative strengths of this. And this is the idea of our saying, okay, changing that W1. And you can see here, it actually did a pretty good job. After like 150 times, we call it epochs or epochs, basically saying how good it is. And this is our loss right here, I was saying. This loss represents saying how good of the model it was. Okay, so you can see it's pretty good, right? If we have something more complicated though, you can see here, it'll try its best trying to figure out what's going on. And it'll try, you can see it's trying right now, it's getting its training loss still 0.36, and you can see it's getting a little lower, and it's getting there, but you can tell, like, it might take a long time or it might never get there kind of deal. And this is where we can actually add more complexity. So for example, if we added more of these extra nodes, and let's just add these extra hidden parts, and I'm just gonna pack it, you can see how this can get very complicated and stuff like this. And it's like, okay, well, let's just try this. And I don't really know if this will work or not. We can try it forward and say, okay, like, let's see how it goes. Like, all right, it's taking some time, and you can see it's starting to get it, give it some time. This training loss is about 0.2. Like, eventually we want that training loss to actually be as 0 as possible, right? Basically saying it's got it figured out. Okay, so you can kind of see, like, okay, I didn't quite get that re-error. It's kind of got the general shape though, if you look at it, right? It's getting more or less right. So you can play around with the structure and figure out, what you should do and everything like that. You can see over time it's getting small, and then it's trying out new things, so it gets a bad error. So that's kind of the concept here. This is one that I kind of put together already that has this, that I saw that works pretty decently. And you can see here all the different weights, and you can see how complicated this stuff is. And you can see some of the weights have almost no value onto it. But then after some time, you can actually see it do a pretty good job. And in fact, it looks like it got pretty much to this point where it's not making any mistakes. And you'll notice that it's not still perfect because, like, I mean, perfect in the sense that we intuitively probably understand, oh, ideally we should just color this blue and this part orange. But there's a little bit of a leakage here. I see it kind of fluctuated, trying to make, it tried something new. That's why I kind of did that little big jump. But before that point, we actually saw that it does a pretty good job. So I'm actually going to reset this, and, oh, it did a pretty good job at that last point. But we'll keep trying something new until it works out well. So if I give this enough time, eventually it'll do a decent enough job. So we can see here, if I pause it, you can see there's some weird breaks right here. And that's because it makes sense. There's no data for it to tell. Okay.
Is there, like gradient descent, is there steps, like input that you add just so it doesn't, like, go on forever, or you just wait?
Yeah. And this is where actually you would define these things ahead of time. So one is like, for example, how low of an error do we need it to be? We could stop it there. We also could say for this epochs, you could say, okay, only go for 1,000 or 10,000 or 1,000,000 epochs and stop there. That might be something you can do too. A lot of times too, like, you can see, like, when we had a really good model and then all of a sudden it jumped up because it tried something new and it did really bad. you can store basically your best model. Say, what's the best model you've done so far? So even if it messes up later on, you can say, okay, well, stay out. That's your baseline, but keep training and trying to figure it out. And basically, you just give it enough time, and eventually, hopefully, the idea here is that you would actually get something that's pretty decent going through. And you can see there's a bunch of different like little, like in this case, this is kind of showing you like what other different parts you can have. For example, the learning rate, like you probably recognize that like is alpha for the gradient descent. That's come from what's it called? Or gradient descent backpropagation. So you can see like a different learning rates of what we could do. The activation, that's kind of new, which we'll talk about a little bit. Regularization, we kind of talked about regularization before. We'll talk about more later this week about it. This is just saying what kind of problem we can have, what regression or not. And then you can see like our ratio of training to test data. That's our train split data. So in this case, I did only 70% of the data will be part of training, and then the rest will be part of testing. And there's this new thing called batch size, which basically, we haven't really talked about this, but basically the idea here is that instead of running all of the data through, so like one thing you could do is like run all your data points all the way through it, see how bad all the data points are for your training set, and say, okay, go through, and then back propagate all the way back through, which takes a lot longer than it does for feed forward. And they say, okay, then go right through. Well, if you have a lot of data points, it might take a long time to do just one run. Like, imagine you have like 10 million data points. And you're like, well, cool. But now it has to take a long time going through. You might make a batch size that's relatively small and say, okay, only take in this number of things, pass it through, feed it forward. And it's like, okay, cool. That part's trained, one time. Let me go take a new batch and pass it through, go through. And basically you keep passing in different batches. So that way you don't have to train the model over all the data at once. But you can do it in little batches. So that way it runs a little bit quicker. And what it effectively does is you'll not go to, essentially we're looking for the, kind of jumping ahead a little bit, but like what you're gonna do in this neural network when you do backpropagation, essentially your backpropagation is trying to find the quickest way down the local minimum or the global minimum of your cost function. So your cost function is some weird function, and you're trying to basically go down with gradient descent. And what's interesting is that by having basically your batch size at 100%, so like you do the whole batch of everything, you will very carefully kind of like go down this hill exactly like where the best value is. But if you do a batch, it turns out you have much more like someone who's, I heard it best explained like someone who's really drunk, and like kind of like sometimes they go downhill, but sometimes they're kind of going uphill or not going the best downhill, and they'll take very quick steps. But because you're doing very quick steps, for the most part, you might actually end up getting to the bottom quicker and more easily, versus if you take very careful steps or very small steps every single time, it could take you a very, very long time. And that's also kind of part of your learning rate too. So there's a couple of things, like basically you can think of your learning rate and your batch size, basically saying how quickly do you get there. And basically this batch size, for example, just if you have a low, very, very small learning rate, you'll get there, but it might take a very, very, very long time to the point where it's not worth waiting. In a batch size, if you have a very large batch size, you can get there, you know exactly what's the best option to go, but each time it's going to take a long time for it to process through. Okay, so this is kind of like, I think this is a great one that they had put together, TensorFlow, to kind of show you the idea. And you can see, like, for example, what each part is essentially focusing on. So you can see like each like perceptron, essentially, each node here is focusing on something different. And basically those weights, and you can see all these different weights, for example, like some weights are very, very small and some are very, very more important. You can see right here, for example, at the very end here, it has more of this of a swirl right here. And it says this swirl is very, very important. And so you can see it's a very, very large value to say if it's, in this case, blue or red or orange. Okay, so cool. So I would say, like, I would say come back to this and say, okay, that's kind of how it works. I think this gives you an intuitive, like very quick, like what's going on. Of course, we're not going to just do it this way. We're actually going to be doing the mathematics and actually the code itself. Okay. Any questions you got on this, or what's going on?
No, I think I got it.
Okay, cool. Again, I think it's pretty sweet. Pretty good visualization. So I am going to, I don't know why I clicked on that. Okay. I'm going to show you a little bit from the curriculum because I think that's just easier for me than me trying to reproduce it for you guys. They kind of give an example of like detecting like if it's Santa or not. I don't think that's actually the best example, but whatever, it is like, you know, saying like, oh, is it a Santa or not? And basically you can say each part of these features right here, like I said, like this X, this you can think is X1, X2, X3, all the way through. And essentially right here, this X1, this is the notation, this X1 on top, X2 on the top. This is basically saying each of your samples. So like each column here is a sample, and each row here is kind of like each part of those features, okay? And at the end of the day, you basically have on each sample, it's either Santa or not Santa, 1 or 0, okay? And that's what this matrix represents. This X right here represents saying all the training samples, or I should say all the data samples itself. And then this Y here is all the training samples outputs, like their true labels, what they should be, okay? So you can see that neural networks are a type of supervised learning, okay? So, and then it kind of goes through a little bit saying like, you know, like how you can do this. So I mentioned about the sigmoid function. Basically, you can put every value in here into this function, 1 divided by 1 plus e to the power of z. It's represented by this sigma, this lowercase sigma right here. This is the classic sigmoid. For the record, most of the time we don't use sigmoid anymore. Sigmoid tends to be considered old school. It's good, but we found better functions that do this. But the main idea is you have something called an activation function that says, all right, either 0 or 1. And you can kind of think of this like in the context of like a neuron, whether or not to fire, like whether or not to be on or off. But you can notice that even though there's like close to 1 and close to 0, there's also some like leeway right here. For example, there's about a 0.5 here. So you could have a neuron, or not a neuron, but a perceptron, a node, actually give something that's between 0 and 1. But the idea here is like, okay, like you can think of 0 being like, oh, absolutely not. 1 being like, oh, definitely yes. And between there being like, oh, maybe. It's like, oh, maybe not. Okay. And this is your activation. So here's another diagram that's kind of similar. You have your inputs times your weights. So there's your W1, W2, and all this stuff for all your different features. Okay, so you see there's L different features for this one sample. And you put it into right here, into your node with your bias, and you can say, they put the little sigma here saying you sum it all up. Basically, you do x1 times w1, x2 times w2, and so on, add them up plus the bias. You get some value here, you pass it through an activation function, in this case the sigmoid function, and then you get an output between 0 and 1. And that output then would then be used the next layer over, okay, like we saw from before. And so this kind of says, okay, this is the basic function for each part of those nodes. So if you think back on like this right here, each one of these nodes has exactly that. Basically taking all the inputs plus the bias, summing it up, pulling an activation function on there, which sets it up to 0 to 1, okay? And then it'll pass on to the next like layer going forward, okay? And it keeps doing that through until it's done all the way to the very end, okay? So what comes down though, is that after you do this, you actually have to say, well, how good of a, what's it called? How good of a function was it? How good of a model was the network? Okay, and this is where we actually have the loss and cost function. And essentially here, you can see here, like this right here is our cost function, usually represented with J. I don't know why it's represented by J, but it is. You can think of like the L right here, basically we're summing up all of the loss in here. Basically how different, and this is where you can see this L is usually represented like meaning that this is the loss itself. There's different ways we can do the like what kind of loss it is and stuff like this, but generally this is the best one right here that we tend to do is basically taking this log part. And the reason why is because if you have y to be 0, right? If y is 0, then that means that it's not y, or it's whatever the no is. So this would be 0, and then it would be 1 times log 1 minus the y hat. So if y is 0, you would want this to basically be 0 as well, this loss. If it's 1, you want this basically also to sum up to 0. So if it's anything off of 0, then you know basically how wrong you got it. How wrong did you get it? This loss function can be adjusted, but this is typically what we tend to do. This is kind of a cool little mathematical trick that we've written out. But once you know the loss function, you say, okay, do this for all the samples. So you see from, what's it, L number of samples, okay? You say, okay, all this number of like basically rows, and you say, okay, or I guess columns in this case, but basically all your data points. And you say all the loss function, you say, are all the loss, sum it all up, basically take what the average is, and that essentially is your cost, okay? And your cost function is really kind of like the idea of saying, if I use these weights and this W here, you really should think of this as a vector or even a matrix. And this B here being the bias. That's like, okay, using this W and this B, I'll get a Y hat. And what kind of loss will I have from this function? So you can imagine this really complicated function of, depending on how you adjust the W's, how you adjust the B's, of how good your loss function will be. Because it's deterministic in that sense, right? Like if I have a W and I have a B, I can know exactly what the model will look like. I can pass the values through there and I'll know exactly how much the data will be off of this actual labels. And that will give us our cost function. So this big old multi-dimensional like beast of a function, J right here. And what we can do here is like, well, okay, we want to find the minimum cost. We want to make the cost as small as possible. Basically, we want the loss to be as small as possible for each of the elements. So you can see here, it's like, well, the gears start turning. It's like, wait, we have this function that can determine what's the best model. If we know where the minimum is, we know what W and B are. So we just need to find what the local minimum, what's the smallest amount of loss we can get. And we can do that with gradient descent. So essentially what we can do is say, okay, we have the function right here. Cool, okay. So we have the function, then all we gotta do then is take the derivative, right? And basically use gradient descent to figure out, okay, let's go take the derivative. We take derivative at this point and say, what direction should we go? Should I nudge W1 in this direction, judge W2 in this direction, and figure out what the fastest path downward is. This is why for batches, for example, you can see this might take a long time. You have to essentially use the model, essentially create the model with the WBs, which is not hard to do, okay? You calculate this part, but then you have to judge it against each individual data point, subtract these off, and then figure out this part, but then take the derivative of this thing, okay? And then basically readjust the model's parameters, and then go forward and do that over and over and over again until you basically reach the minimum or close enough to the local minimum or global minimum. So that's essentially what's going on here. So just to kind of quickly show you is that this one, let's hear, I think they're actually not showing a specific function, but you can imagine this function here is that this is the minimum, is that we want to travel down this part based on, and this part right here really is the cost function. So this is the shape, and this is only a 3-dimensional, but obviously you can imagine like with many, many parameters, it could be like a 15,000 like dimensional object. So in a lot of ways, it's not the best way to kind of picture it. The way I kind of think of it is that you're adjusting the W. What way do I have to adjust the W to make the loss smaller? Okay, basically, how do I make this this cost function smaller each time? And gradient descent basically tells you how much you should dial each individual W and each individual bias. How much should you adjust that dial to move closer to the local minimum? Okay. So does that make sense though, between this loss function, the cost function, and the gradient descent of what we're going to do?
I'll have to go over the math a little bit more, but I understand it like in reference to gradient descent.
Mm-hmm. Yeah. This part right here, like this one right here, just know it's just a fancy way. Like we could have done anything we wanted for the loss function, basically how different it is. Basically just it's a smart way of being able to say, oh, when y is 0, we want it to be 0. So you imagine if y is 0 in here, this will be 0. Oops, shoot. There. So you can imagine this will be 0 right here. This one will be 1. So all we really care about is log 1 minus y hat. Well, y hat is between 1 and 0, right? So if log, for example, is, if y hat is 0, then it's log of 1, right? Well, log of 1 is just 0, which means our loss is 0, which is good. That's as small as we want it. Basically, our y hat was perfect. But if y hat was like closer to 1, we can see we get log of 0, and log of 0 is not very good. Log 0 is basically close to infinity. So essentially, we have basically a very, very large loss function here. So like, oh, you're completely wrong. Like you're not even close. Okay, and if you did the same thing with like saying y is supposed to be 1, you can do the same thing and see how far difference it is. So basically, this allows us to adjust, say, how far away were you from this one specific instance based on your model. Okay, and then we essentially, once we have that, say how bad were you, we just sum up how bad you are. That's what our loss is. It's saying, how bad are you? And then our cost function is saying, how bad are you overall? Okay. And then once we have that, it's like, okay, cool. We just need to take the derivative of this, which turns out to be a little more work. And this is where, what's it called? Our back propagation going through. So our back propagation is probably the more complicated part. And this is where like you have like all this notation, for example. I would actually suggest a specific video that does a really great job explaining this. I would actually say, like, I would say, how to say this? I would read this through and try to follow along all these different notations, because I can kind of walk you through it, but basically it's the chain rule, each part. So you can notice, for example, you get the dy hat here, dz. Basically, we're trying to figure out how does the loss function, well, really the cost function, but how does the loss change based on, what's it called? Based on how we change, well, essentially the W1s, the W2s, the bias, basically how does that loss function change? If we know how the loss function changes based on what parameter tweaks we do, then we know how to travel down that mountain. So essentially that's what's going on here. We basically would do, you can see like this dwy. Basically it's saying we take the derivative of the loss function with respect to our model. And our model represents basically all of the W's, all the biases, right? And you can see here, for example, W1, W2, in this case it's W or DV, so it's biased. So we're trying to figure out like, okay, how do we find this derivative, okay? And this is really what we're trying to do right here. Like this is mathematically all it is. However, trying to figure out like, well, how does DL basically change by the weights, okay? And that's when we actually have to do the change function, because remember, there's multiple parts in there. So each part affects each other. So you essentially have to kind of work backwards, starting from the very end of the loss function and say, okay, how does it get affected based on the very first W or W1? And it turns out, like, it sounds like that would be a whole lot, but it turns out because they're so similar, in a sense, each node is relatively simple. There's not like really complicated parts. Basically, you keep repeating the same process. So once you understand it for like essentially one node, you just keep repeating it the same way. And this is why you can do it basically with all these different like, notation. To be honest, the hardest part is probably the notation, just following, making sure you're looking at the right thing. But basically you can follow this along. You can see this derivative. There you can see this part right here. But this is essentially, once you have this derivative and you understand how to, like when I say understand, you code in basically how to adjust it, you have the gradient descent by itself. So I would suggest is a specific YouTube video or actually the YouTube series is 3 blue, 1 brown. And then I think he actually has like 4 like videos on it. So let's see here if you have it right here. Well, this is, I thought he had a playlist. Well, anyway, basically there's these different videos right here. I think he actually has the playlist on here. Let's see if I can find it really quickly. Let's see here, playlist, exposition, no. Here's neural networks. So I think there's only like 4 videos. Oh yeah, 4 videos. And so right here, like this is probably about like a little bit over an hour's worth of time, right, of watching these videos through. But he does basically like what is a neural network, which is more or less kind of like explaining the motivation behind it. And basically this is the part, right, the gradient descent and then calculus propagation between, like this is when he actually shows the mathematics, which I think he does he does such a great job. Like I won't make you watch this, and of course it's a little ad, but I just want to kind of show you, like he shows like the full process going through. And I think if you follow along with this part, like if you watch all the videos up until this point, like it looks very complicated right now, right? But he does a really good job of like slowing it down. I would say like pause it, rewind it. And if you can understand what he's doing each part, you basically know what the gradient descent is. He does, I think, like probably one of the best ones, a mix of like explaining like how it works, but also showing, what's it called? Like showing the mathematics and being able to actually say, look, this is how it works. So I'll make sure to send you this playlist specifically. But if you watch this through, you'd basically be ready for between now and tomorrow's study group. I think this would be pretty good. Okay. So I'll make sure to send this to you, Assad, and I'll link it in the recording too, in case you want to look at it later. I'm just looking at the section. You can see here basically the deep neural network. It's the same thing. It's just saying, oh, instead of looking at just one process right here, it's like, what if we repeat this over multiple times? It's like, okay, if we repeat it multiple times, you'll actually have this part. And then it talks about the different activation functions, like sigmoid, tanh, ReLU, leaky ReLU. Basically, these are different ways to set the function to 0 to 1. So you can see here, for example, this is a sigmoid that shows in the very quick example, the hyperbolic tangent. You can see it's a little bit different. It's a little steeper. ReLU, inverse tangent, but then ReLU right here, this guy right here, rectified linear unit, which is just pronounced ReLU. You'll see basically 0 and then 1, and just increases upwards. Note that there's also the leaky ReLU where you have a little bit of value. This one and this one, the leaky ReLU and ReLU, are probably the most common ones used currently for machine learning. Though tanh sometimes is also used, but sigmoid is considered old school. The reason why it works fine, but it usually takes longer for the training. Basically, just there's a lot of reasons why it doesn't work out, but just know that sigmoid, they all technically work. It's just more like, people tend to have a preference in the sense of what they see works well, or quicker, I should say. Okay. So cool. That's all it is right now for this session or anything like that. Do you have any questions, Hassan?
No, I think I got the concept of it. I just have to go through and read through the math a little bit more, watch those videos.
Yeah, the math is probably the hardest part. Like this is nothing really special. The math is probably the most difficult part, trying to follow it through. That's why, honestly, I think reading is one thing. Like I suggest reading it through, at least the first time, and just see if you can kind of follow along. But I think there's something to be said to actually watching someone do the derivation of where these are coming parts. And I think he does a really great job of doing that, especially if you watch, like I said, it's kind of long. It's a lot to say for an hour. But I think this first part, you can probably watch this very quickly. It's pretty much what I explained. But between gradient descent and then into this last one, this will really help you. I think that one's perfect for the amount of explanation. So cool. All right. So yeah, and then we'll continue this for tomorrow's study group on more deep learning.
Okay. Cool. All right, sounds good.
All right. Cool, son. All right, I'm going to stop recording.